Okay, thank you. We will start again for our last talk on the art of counting. So, Professor Meel, you can start.
Right. Good afternoon, everyone. So, first of all, thanks, Florent, for inviting me. It's my first time in Montreal, so that's been fun so far. I want to talk about the problem of counting. I'll talk about two approaches that the community has taken over the years. This is a problem that I have been working for a long time. I noticed the first paper I wrote was about 14 years ago. So this has been the problem that I have worked for last 14 years. So I'm very, of course, excited to talk about it. Something else I want you to cooperate with me is that please ask questions as we go along. Okay, so don't wait until the end. I prepared some slides. I'm sure we'll be able to cover all of them, even if you ask questions every minute. Okay, so please. And what I usually do is that I have some quiz at the end, and it would be very embarrassing if you don't get it right. So it's better that you ask question than to get embarrassed. Okay. All right. So just to give a bit of a brief overview of where the problem sits. So this is the end of the today's session. A lot of approaches that we have talked about lie in the area of automated reasoning. How it started long ago, you have some systems, some properties, and you want to reason about whether these systems satisfy the properties or not. One way that we have found useful over last 70 years or so is to model the systems using some logical formalism, the same for these properties. And then, of course, one of the natural problems that arises is that is there an execution of the system? For example, is there an input so that the output that the system produces violates the property? So instead of checking whether it's always satisfied, you can turn and ask whether it ever falsified. So this becomes the question of satisfiability. Satisfiability is, of course, a fundamental problem that has been studied even before the computer science as a field originated. One of the simplest formulations that you have seen since morning, you have a formula. Is there an assignment that makes the formulas evaluate to true? We know this is a hard problem, and what hopefully is seen throughout the day is, well, it is hard in theory, but not so in practice. And over past few years, we have developed these really powerful solvers that can solve problems involving millions of variables. The area that I work in, the way we kind of read NP as not a problem. Okay, so what happened by 2010s is that we had these really powerful set solvers. So the question became, let's go for the problems beyond satisfiability. You've already seen a bit of flavor of that looking at the problem of max set for some of the talks. I want to talk about a slightly different problem beyond satisfiability. So in case of satisfiability, you want to know whether the problem arises is that whether the system ever falsifies the property. But sometimes you want to measure. Instead of asking, do you ever leak information, how much information you are leaking? Are the systems fair? How robust these systems are? You have some critical infrastructure and you want to know how resilient it is, let's say when a hurricane strikes. So the flavor of questions here becomes that of trying to quantify. So you want to know how often the system satisfies the property. And that becomes a counting question. So we have gone from, does it ever satisfy? Does it always satisfy to how often it does? So let's try to formulate the problem in simple terms. So we have a formulas. Almost all the discussion we are going to do will look at a Boolean formula, but a lot of these things hold over to more expressive constraints. So let's say you have a Boolean formula over n variables x1 to xn. Let's say sol of f is the set of solutions of this formula. The problem of satisfiability was to check whether this set is empty or not, right? Whether sol of f is empty or not. And counting is how many solutions there are. Okay, so just to make sure if you had coffee or not, Suppose the formula is x1 or x2. What are the solutions of this formula? Well, all the assignments except 0, 0. So there are 3 satisfying assignments. So a counter should be able to answer 3. Okay. We can lift this problem to arbitrary weights. So we can have a weight function that maps every assignment to a weight between 0 and 1. And now, instead of summing up the number of solutions, we are summing up the weight of each solution. And now the problem becomes, well, given a formula and the weight function W, what is the weight of the formula? For most of the technical discussion on for techniques, I'm going to focus on the unweighted case where the weight functions assign the same weight to all the solutions, but a lot of these techniques also live to the weighted setting. Okay, so what I want to talk about, first I want to kind of give you a flavor of, what kind of problems that we can model using counting and how does this modeling goes through. Then I want to talk about 2 approaches towards solving this problem. These are 2 different areas. In each of them, of course, my collaborators and I have been developing specific tools. So these are the 2 tools that we have developed that belong to 2 of these different approaches. There are, of course, other tools that have also developed using these approaches. And then finally, where things go. Okay, so one of the problems that we have looked over the years is, in a city, I did my PhD in Houston. So Houston was prone to hurricanes. And one of the things people there want to know is that what's the likelihood of a blackout if there is a hurricane that strikes? If you ever found yourself in a hurricane, it's no fun to be in a hurricane and also have a blackout. So you want the city authorities to be able to predict these probabilities so that they can plan accordingly. So how is this problem related to counting? Well, there's a critical infrastructure. Let's say we are looking at a power grid. There are some nodes that generate power, some nodes that we care about. So let's say there's a set of source nodes, a terminal node T that we care about. Given a certain category of hurricane, you can assign failure probability to different edges. So what is the probability the edge will fail or not? And now the question we are asking is, what is the probability T is disconnected from the source? Connectivity can be written down as constraints, same for the disconnectivity. And if you think about assigning the same weight to all the failure probability, same probability to all the edges, then we are interested in counting the number of subgraphs where S and T are disconnected. Otherwise, it's the weighted counting problem. So this is how the problems happens. Like you take this graph, you can write connectivity using constraints, and now you are trying to solve the weighted counting problem. Techniques I'm going to talk about has allowed us to obtain rigorous estimates for medium-sized cities, which were not feasible in the past. And this is a very well-studied problem in civil engineering. Another kind of applications I have been trying to look at the kind of properties we are going to care about now that we are increasingly designing systems that have a statistical component to that. So one such application has been that what we discovered about 10 years ago, there was some hope that we'll design the systems and there would not be any robustness. Now we are kind of realizing they are going to, that they would be adversely robust. But now we are realizing that, well, there are always going to be such cases that you make small perturbation and you can fool the system. So now the questions have become how robust these systems are. So again, we want to, given an epsilon, we want to quantify how robust these systems are. So the question has gone from satisfiability to that of counting. Again, what you can do, how to encode this as a counting problem? Well, you model the system symbolically, and now you want to count how many input there are, so that if you make a small change, it gives a different output. You can also put a probability distribution over the set of inputs you care about. Similarly, the problem of fairness is again how often it is the case that if you were to change some sensitive attribute, you would get a different output. Again, from a symbolic perspective, these are exactly the same problems. Quantifying over the space of possible inputs, you can put a probability distribution. So I talk about these two applications, things that counting has also found lots of other use cases. For example, for systems, you want to quantify what is the information leakage you are observing through side channels. This is where counting is now one of the dominant approaches. And there are other applications such as partition function estimation coming from statistical physics, or you are trying to do testing and you want to estimate how much coverage you obtain. I'm around for rest of the day, so we'll be happy to talk about these other applications. So look, if there's a problem that has many applications, then there has to be a flip side to it, which is that it's hard. We know counting is hard in theory. In fact, Leslie Williams during our citation quoted his result on Sharpe hardness. So Sharpe is the class of counting problems whose decision problems lie in NP. So if you thought NP was hard, welcome to the world of Sharpe. This is significantly harder. Stockmeyer in 1983 proposed this idea probably approximately correct. So where in addition to the formula, you also allow two more parameters, epsilon and delta. We want an estimate that is within 1 plus epsilon factor with confidence at least 1 minus delta. In theory, we know that polynomially many calls to set oracle suffice to get an approximate estimate. If you think, well, we already have powerful set solvers, so why was this not already resolved? Well, the thing is that set oracle is not the same as set solver. We have powerful solvers, but their performance depends on the kind of formulas you give to them. And these results don't translate to practice because the kind of queries they want to make cannot be handled by the kind of set solvers we have developed over the years. So a lot of work here has been in case of approximate techniques. How do you design algorithms that can utilize the power of the underlying set solvers that are out there, these conflict-driven, closed-learning-based, CDCL-based solvers? Okay. Just to give you a snapshot of how far we have come in 14 years. So 14 years ago, if you looked at the landscape of counting techniques, so either we had some techniques that could scale to large instances but didn't have any kind of guarantees, or we had some techniques that did have some theoretical guarantees but struggled to scale. Now we have had a lot of work and have been able to develop these techniques that can scale as well as have strong theoretical guarantees. Just to drive home the point further, if you were to look at these robustness instances that I talked about, a 2012 technique on 2025 hardware would be able to just solve one instance. Techniques that we have right now can solve about 900 to 1,000 instances. So there has been a significant improvement in the capability of these techniques. And of course, the entire focus in our subfield has been that can we bridge this gap between theory and practice. We want to develop techniques that have strong theoretical guarantees, yet be able to scale to large instances. I want to talk about two complementary approaches. So one is going to be based on exact counting, where we try to count exactly. And we'll see that sometimes we can scale, but sometimes we cannot. And in that setting, we are going to look at approximate counting, where we are going to trying to get this epsilon delta guarantees. And there are two ideas that really drive home the development of techniques here. For exact counting, you want to somehow exploit the structure that might be inherent in the problem. For approximate counting, we are going to rely on this idea of random hash functions. So let's start with exact counting. There is kind of one way that I like to think about. So suppose you go to a restaurant and you want to know how many possible lunch plates this restaurant could serve. So for a lunch plate, let's say you are going to have one appetizer, one main course, and one dessert. So, well, you can look at the menu, and let's say the restaurant has two menus, one for vegetarians, one for non-vegetarians, and you can't mix and match. Okay, you had to order from one of the two menus. So one way you could do is that you could just start listing out. You could say that, look, I can have, spring rolls with paneer tikka and ice cream. That's one option. Spring rolls with mushroom pasta and fruit tart and so on. I'm vegetarian, so I started with the vegetarian options. So you could start listing down all sorts of possibilities. Well, it's going to take a while, right? Because you can see that there will be lots of options where you will have spring rolls first. And this is the approach that's about enumerating solutions. So you have a powerful set solver and you can ask it to find a solution. And you can just go one after the other. So enumeration can take a long time. What else could we have done here? So the first thing is, what I want you to see is that this approach is going to work out, right? You can just list out all possible plates you can possibly order, and eventually you will exhaust all possibilities. What else can we do? Remember?
All the items, put some constraint, for example.
Well, you already have the menus. Let's say you had two menus, each had 3 pages each. The first page lists the set of appetizers, the second page lists the set of main course, third page lists the set of desserts. And you can order whatever you want. Yeah. What should we multiply?
The number of appetizers that we have times the number of pages.
Number of appetizers, because we had two menus. So what should we do? Sum them up and multiply. Within each we can. So we had two menus. So one possibility is that for each of them we are going to count separately and we want to sum it up, right? And for the vegetarian option, you just multiply the number of appetizers times the number of main course dishes times the number of desserts. Right? And that's it. And this is kind of all we do when it comes to doing exact counting. You want to do two things. You want to figure out some way to break down problems into sub-problems. And then somehow if you could solve each of them separately and multiply things. If you think about, we are trying to do counting. So instead of just listing out all possibilities, you can look at the menu, you can see how many appetizers we have. So we did some counting here, right? We still had to go and count the number of appetizers we had, count the number of main courses and the desserts. But those were simple counting problems. And then we multiplied things together. And then we did the same for the other sub-problem and we summed them up. Okay? This is kind of what we want to do with given a Boolean formula. So let's try to see how can we divide problems. So here we said that, look, there are vegetarians and non-vegetarians. There was a way to divide. What can we do to make to achieve similar division for a Boolean formula? Going back to our setting, you have a Boolean formula F. So something we want to do, just like our lunch plate, we want to divide into two groups. Vegetarians, non-vegetarians, and they won't overlap. So what can we do here? Yeah.
Well, we have A as suppose we look at, in this case for the restaurant, try to
distinguish two types of foods that are, for example, the vegetarian, two types of people who have different interests in food.
Yeah, but here we have a Boolean formula. So how do we take this insight and apply in the context of Boolean formula? How do you divide into two subproblems so that if you were to count their solutions, you could just sum it up?
Maybe is the person vegetarian, and after that, what is the
So remember, it's like taking some attribute and then looking at different assignments that you could have in the attribute. So in case of Boolean, in our formula world, you have variables that take value 0 or 1. So maybe we should count how many cases where x1, some variable takes value 0, and the other setting where it takes value 1. Can't be harder than that, right? So figure out some variable, you branch it. What about this idea here? Where we could somehow just multiply things together. When can we multiply things?
And not satisfying the formula. Use the power of the multiplication.
So one setting is if you could just satisfy by assigning a small number of variables, others are not needed. Let's try to lift this idea in general setting. What does it mean? So something about the Boolean formula, at what point you can just multiply things. Suppose you wanted to find number of solutions of this big formula. You have ideas on how we could try to do better here?
X1 or X2 could be vegetarian, not vegetarian, and 3, 4, 5 could be a cluster main course dessert.
Or something else, something that allowed us to multiply. So
there's somebody in the chat saying variables are assigned values independently.
yeah, exactly. So we want to capture this independence idea, right? Look, if you look at this formula here, you assign any assignment to x1, x2. You could combine with any assignment to x3, x4. That was really the idea between these appetizers and main courses, right? Any assignment over here could be combined here. So if we had a formula where we could divide into small formulas so that they did not share variables. What is the property here? If you look at this formula and think of this as f, or let's call it g and h, then the property here is that the variables of g and the variables of h is empty set, right? There's no intersection between the two. So if we could at some point detect that, oh, in this formula, I could get into small components and they don't share variables with each other. Then what I'm going to do, I'm just going to count each of those components and then just multiply things. And that's kind of the entire exact counting process. Of course, to make things work, if you ever seen a set solver code that involves thousands of lines of code, is you have to do all these things very fast. You have to quickly figure out how to partition into what variable to pick so that you get two subproblems. Then quickly be able to see if there are these subproblems where you can count each of them separately and multiply them together. Yes.
From the chat online, basic divide and conquer principle.
Yes, exactly. Is there a question? Yeah, but yeah, that's
I think
it.
they're just answering your question.
Yeah, that's okay. Then I think if maybe you read out if there's a question. Okay, so this is kind of two properties. They are also called determinism. So if you have two branches which do not overlap solutions, then this is a classical property in computer science we study in many forms. This is determinism. If you think about classical automata concepts, then non-determinism is where two things may have the same witnesses, right? So this is property of determinism. And decomposability is the property when the subformulas don't share variables. Well, now we can try to do things smarter. So something we can do is that suppose you found some subformula, we counted the number of solutions. Maybe we can keep it in the memory so that we can reuse it some other time. Maybe we'll be asked to count similar subformula again. Remember, we are going to start with the formula, assign variables, go to some subcomponent, we count. Maybe you make other assignments and then end up in a similar subformula. So we can start making use of cache. So what we are going to do is that every time we count, we will also have a cache where we'll store this formula. How to store? There's a lot of work. What's a good way of encoding a formula? Formula can be viewed as a graph. What's a compact way of hashing the graph so that the lookups are fast? So once you look at these conceptual ideas, now things become data structure problems, right? How do you do this so that you can handle a formula involving millions of variables, where you'll be making the trees are going to be humongously large. You will have cache entries, hundreds of millions of cache entries. So you want to be able to do lookup, saving cache quickly. You will probably run out of space in cache. So you have to come up with a heuristic, which will be like, how do you clear your cache? So now it becomes kind of all the data structure problem that we often talk about in computer science, right? So the high level idea is that figure out a variable. There are branching heuristics. This is bread and butter of set solving. Set solvers, max set solvers, all of them had to figure out what variable to branch on. Similarly, we had to develop branching heuristic here. Once you branch, it may propagate because you have branched on saying x1 should be 0. Maybe some other variables get implied. So do a quick propagation so that you simplify the formula. Then check if we can identify different components. If yes, then solve those problems separately. Solve each of the problem. Store it in cache. Come up with an efficient encoding of the cache so that you don't have to repeat the work in future. And then combine and go to the other branch and do the same thing. And finally, we'll be able to count. Look, this is just finding satisfiability is NP complete. So are there cases where this is going to not work? Yes. But lots of formulas that we care about are coming from systems we built. So there's a lot of structure there. They are not random formula that just originated. So there's a lot of structure is out there. And that structure is what we are trying to exploit here. This top-down I think let me just we already talked about this. We also talked something else is like, how do you find the small components? You can do graph-based search. And as I mentioned, that for us to do all of this, we'll have to figure out, good way of doing propagation. We have to figure out a good way of learning clauses. Along the way, you might learn implications. You can store them so that you don't re-explore the same space where there are no solutions. We should have branching heuristic. We should do watch literal. So everything else that we have done in case of set solving also applies in the context of counting. Of course, the same heuristics may not carry over. So in this case, we had to come up with different heuristics, but similar idea. Here we are trying to explore the entire solution space. If you look at the trace of what these solvers are doing, or what these model counters are doing, those traces define languages, and that relates to another area in knowledge representation called knowledge compilation. How do you take something, knowledge in one language, convert into another language where reasoning might be easier? And the traces of these counters correspond to those languages. So there's a lot of rich connection between knowledge compilation and these top-down counters over the years. Okay, so this is how kind of it works. You start with a formula, you propagate. If the formula is empty, of course. If there's a cache, then of course you should look at the cache. If you can divide the formula into components, then you divide the formula. Otherwise, pick a variable, count for the two subcomponents, and then you count for each of those and return the count. Okay. So on a high level, this is kind of very simple algorithmic approach. Of course, the devil is in details to make it really work well in practice. What we have found over the years, there are lots of problem settings where this approach works really well. You have formulas involving tens of hundreds of thousands of variables, and the counters will take less than a second to give you the count. Okay. But as you can guess, there are also formulas where this approach struggles, because at the end of the day, it is going over the entire solution space. So even if there is some part of the solution space that is hard for this set solver kind of techniques, we are going to struggle. So can we come up with another approach that does not try to explore the entire solution space? And that's where the approximate techniques come in. Okay, so the way to think about this approach is, maybe like after lunch, it's about coffee. So here's a kind of a puzzle that I like to think about. Suppose you wanted to figure out that how many people in Montreal like coffee. If my Wikipedia search this morning is correct, the population is 1.76 million. Let's say you can assign everybody a 21-bit identifier so that we cover all the people in the city. So how would you go about counting how many people like coffee? You can sample. Maybe you take a sample of, let's say, about 50 people. You figure out how many people like coffee and scale the count. What can go wrong? Sorry? There can be bias, right? Going by kind of quality of coffee this morning, maybe there are not too many people who like coffee. So suppose there are only 1,000 people who like coffee. So we won't find anyone in our sample of 50 people. And we might think it's 0. 0 is very far from 1,000. Right? You can run a good coffee shop with 1,000 customers, but you can't run with 0 customers. So this is kind of where we want to rely on the power of set solvers again. What can a set solver do? What is the corresponding set query? Well, the query is find me a person who likes coffee. That's a satisfying assignment. Or the solver can also say, look, find me a person who likes coffee and the person or person Y. You can also try to enumerate. So again, we know that one way to use the power of solvers is to enumerate solutions. If there are only 1,000 people, you can make 1,000 queries and be done with it. But we don't know ahead of time how many solutions can be. Look, the number of solutions can be anywhere between 1 to the 2 to the n. Let's say we are only focused, counting is interesting only if there are non-zero number of solutions, right? So we don't know. The number can be anywhere between 1 and 2 to the n. So can we do something there where we don't make more than, let's say, n queries or even log n queries to the solver? The final number can be anywhere between 1 to 2 to the n. Okay? And so the approach goes the following way. So imagine this blue circle is the space of all possible assignments. And the red dots here represent satisfying assignment. So what we want to do is to partition this space of solutions into cells such that the number of solutions across cells are roughly equal. Suppose we could do such a partitioning, and the cells are also small enough. So suppose we could do such a partitioning, then how would the approach look like? Well, you go and pick one of the random cell. Because it is small enough, you can enumerate all the solutions in the cell and scale it by the total number of cells. And that would give us a good estimate, right? So pick a random cell. Since if all of them are roughly equal, then you can just pick one of them, enumerate all the solutions in the cell, multiply with the total number of cells. So what are the challenges for this idea to work?
Sorry, I didn't understand the difference between these and sample.
So the question, the key idea here is that suppose we could partition, right? We are not just picking random 50 people. We want to be able to partition into cells, and then we are going to pick one of the cell. But you're right, it's kind of, yes.
If the division of person are not equal, or we will be more biased to choose where there's more dots.
That's a good point. So can we actually do such a partitioning, right? Aren't we going back to having the same issue that there was a biasness in our samples? Can we make such a partitioning without assuming anything about the distribution of solutions, right? We don't want to make any assumption on the distribution of solutions. So maybe, the people who like coffee would be clustered in one place, or they are everywhere. We don't want to make any such assumption. And it turns out that, so that's kind of the key challenge here, that can we do such a partitioning without knowing anything about distributions? And second is, how many cells should we partition into? So for the first, from the computer science perspective, what we are trying to do is to come up with a function that maps assignments to cells. Well, this is a hash function. So as you can imagine, the deterministic hash function is unlikely to work, because if there is a deterministic hash function, then you can come up with one distribution so that it doesn't do well. Okay. So this is where we rely on the power of randomness. In particular, we rely on the power of what are called universal hash functions or two-wise independent hash functions. So what are two-wise independent hash functions? They say that if you pick any pair of two assignments, the probability that they map to the same cell is independent. Okay, so they are pairwise independent. Pairwise independence is technically suffices for everything that we are talking about, because pairwise independence is what captures the variance. Yeah.
One question on the chart. What is the cell?
The cell here is, maybe it will become clear very soon exactly what the cell is. So just hold off for a minute. Yeah. Okay, so let's actually talk about what is that cell. So we want to map over the assignment space. So that is our n variables. So 0, 1 to the n to the cells that can be represented by m bits. Okay. This is just the range over these hash functions. And in order to do such a partitioning, we are going to construct m random XORs. What is an XOR? It's a parity constraints, addition modulo 2. How do we construct every XOR? Well, you pick every variable with probability half, you XOR them together. And you set all of these to equal to 0 or 1 randomly and independently. And now a cell can be defined as the conjunction of the original formula and these m random XORs we have constructed. Remember, the way we are constructing these XORs are independent of the formula. This point, reasoning does feel a bit like magic, but that's where probability comes in. Things go through. And this is where we want to rely on the power of set solver, because now it's a set formula, right? There's a formula conjunction of constraints. We can give it to a set solver and ask it to enumerate solutions. One thing we haven't addressed right now is that how many cells should we partition into, right? What is that value of n? So let's say technically one thing we had to let's get out of our way is that what is a cell is small. So we'll say a cell is small if it is some about threshold many solutions. That depends inversely on 1 by epsilon. That's not very surprising. If you want very tight estimate, you will have to work with large cells. Okay? There's a bit of a chicken and egg problem here, because if you have many solutions, we want to partition into many cells. If you have fewer solutions, we have to partition into fewer cells. But we don't know how many solutions there are. So how do we get around this challenge? Well, the idea, again, as it is often the case, simple ideas are what work well. You start with a formula and you make a query. You say, are the number of solutions greater than threshold? How can you make such a query? Well, you can enumerate. You can ask for one solution, second solution, third solution. Let's say threshold is 60, so you go all the way till 61. If you found 61 solutions, then we definitely know that the number of solutions definitely greater than 60, right? At that point, we partition into two cells, which means we put an XOR. Remember, putting an XOR and setting it to 0 or 1 gives you one of the cells. So now we are just going to pick one of the cells. We'll make the same query again. Is the number of solutions less than threshold? You enumerate solutions. If the answer is still, there are more solutions, which is that it's not less than threshold, partition further, put another XOR. We keep doing it until we reach a point where the number of solutions will indeed be less than threshold. And at that point, our estimate will be the total number of solutions in this cell times the total number of cells. As you can see, we don't have to go through this one step at a time. This is a bit of a binary search, right? You can make some jumps here. So we can make log n calls. Remember, the number of solutions can be exponential in n. And we are going to make log n calls. So there's double exponential gap in the number of calls we'll have to make to a set oracle. And 1 by epsilon square log 1 by delta, because that's the threshold. So every time you have to enumerate up to threshold many solutions. Okay? Is this idea clear? What do? We start with the formula. Yes. Is the number of solutions less than or equal to threshold? No? Well, partition further, partition further, partition further. And then eventually we reach a point where the number of solutions is indeed less than or equal to threshold. As it turns out, ideas often are connected. This is also very closely connected to what is called an enumerated combinatoric sieve method. You are trying to design some sieves so that you could estimate in one place and extend everywhere. In computer science, we often work via these universal hash functions or independent hash functions. Okay, so I want to kind of quickly tell you, how much progress that has happened over the years. So I just took a snapshot from 10 years ago. So, 10 years ago, if you took the state of this technique that I talked about, approximacy on the instances, these experiments were done last year. So we have, let's say there's 1900 formulas. So the method at that time could solve something close to 600 benchmarks out of 1900 instances. And then over the past few years, we have seen that the progress has increased. So on y-axis, we have the number of instances solved. On x-axis, the time is in log scale. So what we indicate here is that the corresponding method could solve, let's say, about 500 instances. each of them in less than 100 seconds. Okay, so ideally you want to go higher and higher up. Just to put out these numbers. So in 2016, you could solve 600 instances, each of them in less than 1,000 seconds. 2016 solver on the same hardware, okay, from 2025. The method in 2024 can solve 1,291 instances, each of them in under 1 second. If you just take one of the instances to showcase, in 2016, you would take an hour to be able to count the number of solicits. Over the years, the time has reduced and now it takes 0.02 seconds. Again, on the same hardware. This is not due to the improvements in the hardware. So we've been able to, everybody else in the community have attained about 100,000 speed up over last decade. And I still had the same guarantees. And how does this work? Well, I mean, in order to make progress, you have to work along many axes: theoretical advances, algorithmic engineering, and system software development. So developing solvers that can reason well about the kind of queries we are making, improving algorithms or the kind of queries we are making, similarly over theoretical advances. I won't have time to go over in all of the details, but I want to just kind of give a flavor of one such work, which is on system development. So a core problem here is that we want to partition into roughly equal small cells. For that, we rely on this conjunction of the CNF formula and these random XORs. The original constraints are often written in what is called conjunctive normal form, here a set of clauses. So the underlying solver has to be able to handle these kind of constraints very well. These are CNF with conjunction of XORs. The kind of set solvers that you have probably talked about in the morning are based on this paradigm called conflict-driven closed learning, CDCL. CDCL is a powerful paradigm, but struggles for exactly these kind of formulas. In fact, we have theoretical lower bound that if you put random XOR, CDCL solvers are going to struggle very badly. At the same time, CDCL solvers are really good for CNF part. I mean, this is why the set solving has become a practical technology. So what we had to do is to build a solver that can reason about these two kind of formulas at the same time. One, the original CNF, and the second, conjunction of XORs. XORs on their own are fairly harmless. This is, Gauss-Jordan elimination. As linear equations, you just do Gauss-Jordan elimination. On their own, they are fairly harmless. So what we can do is to have two components. One that takes care of the CNF part, the other that takes care of the XOR part. But of course, they can't operate in isolation. They will have to communicate with each other. The CNF part will say, look, I assigned a variable some value. Here is what I propagated and deduced. What do you think? XOR will do its Gauss-Jordan elimination and say, look, this is what I think happens. And then the two have to communicate with each other quite a bit. We are dealing with formulas involving hundreds of thousands of variables, so there will be millions of such communication. If you have to talk millions of times, you better be very efficient. So a lot of work that has gone on is how do you design data structure that enables such efficient communication with each other. This is just one kind of CNF XOR formulas. Of course, there is also a lot of structure in the kind of queries we are making. So can we propagate the information that we had in the first call to the second call so that the solver can do a warm start rather than doing a cold start? So there's a lot of work that has gone on in how do you make these queries very efficient. It's not the case that you always get formula that come out of that are naturally represented in CNF. Sometimes they can be represented in what's called pseudo-Boolean format. So can you lift these techniques that can handle things at pseudo-Boolean level? Or in case of binary neural network, there's a very constrained format in which how the neural network constraints come out. So can you develop propagation and reasoning techniques directly at that level? So there's a lot of work that has gone on that tries to exploit the structure that is inherent in the problem. As I mentioned, there's a lot of work that has gone on, and I'll be happy to talk about, how there are lots of opportunities to also work at different. If you are interested in doing just pure theory, there is a scope for you. If you want to do algorithmic engineering, there is scope for you. If you want to do software development, there is scope for you in the field of counting. Let me just kind of wrap up showing you, does all of this work in practice? Okay. And this is collaboration with civil engineers at Rice University. So this is one of the medium-sized cities from South Carolina. And we wanted to compute reliability of 60 terminals. So this is how the state-of-art technique that is used in civil engineering works. This is based on recursive decomposition of graphs. It timed out on all such instances. What I talked about today, we can compute estimates with theoretical guarantees consistently in under 100 seconds for all such terminals. And as I mentioned, we are able to handle medium-sized cities with theoretical guarantees. In the past, people also, of course, relied on Monte Carlo techniques, but we could also show there are cases where Monte Carlo techniques converge to the wrong value. And this is when we got interest and conviction from civil engineering community. What often happens in automated reasoning that if you improve a technology, then there are more applications. And that's kind of has started to happen. There are now more and more applications coming from computational biology, from cryptographic attacks, and so on. And there's also now we have a model counting competition that has been running now for last 5-6 years that allows lots of people working on this technology to improve their counters every year, share knowledge. These are also open source, so which means that anyone who improves 1 year, everybody else is able to copy those ideas. If you don't copy those ideas, you don't have a chance of winning next year. So it's not a very wise idea to close your eyes. So where do we go from here? Well, as it turns out, there is a lot more now. The application that we are more challenging compared to the counters we have. And I would also kind of say that, today's counters are about where the set solvers were in early 2000s. So I think we need like another 100 factor speed up. How are we going to get another 100 factor speed up? Well, one is that you need some challenging problems because that kind of defines the compass of the community that, look, these are the problems we should be able to solve. So here's kind of 3 problems that I view as interesting, challenging problems for us to target. So one is we can estimate for the cities of medium size, but if you give the power grid of a city like Los Angeles, it's completely beyond our capability. So can we handle a city of that size? We can handle right now a few thousands to tens of thousands of neurons, as Joao mentioned also in their setting, but we want to be able to handle million neurons for quantity evaluation. And similarly, these things are used for information flow analysis where you have a few 100 to 1,000 lines of code. Can we do 10,000 lines of code? This is not just a compute problem. Remember, these problems we are talking about, which can quickly exhibit worst case structure. Okay, so going another 10 or 100 factor really requires new technical ideas. What's going to get us there? Well, some idea that I just picked 3 of my favorite ideas here. One is that what often happens is that we try to translate everything at the bit level, and that loses a lot of structure. In case of set solving community, there's a lot of effort that has gone on in building these higher order theorem provers, which are called SMT provers, on which things like lean and all are built on top of them. So similar idea here would be like we want to be able to reason at high level constraints of SMT. Similarly, for algorithmic engineering, there is a lot of scope that is definitely out there is that how do we improve our heuristics based on the underlying structure that might be in a lot of sub problems out there. And there is some exciting development that's going everywhere in the community, which is that look, we developed a lot of these solvers based on CPUs. Can we take advantage of the new hardware accelerators out there? Some promising work has happened, but a lot more that needs to be done. And finally, another thing that is very exciting and is slowly catching a lot of attention in our community is that we also want to be able to certify. So today's set solvers are amazing at this task. When a solver says that the formula is unsatisfiable, it will also tell you why it is unsatisfiable. It's not just saying that I could not find a solution, so here's my best guess. It tells you why it is unsatisfiable. So we need similar ideas about certificates for count. When I tell you here's the count, exact count, can I come up with a certificate that you can independently check? The question becomes much philosophically interesting. What does it mean to certify probabilistic algorithms, especially probabilistic approximate algorithms? When what does it mean to say that here's the answer and here's some probability associated with it? How do you develop confidence of the user? So we have some work on this, but a lot more that needs to be done here. So with that, I will conclude. I'll be happy to take any questions, and I'm around for the rest of the evening. Thank you.
Sorry. You have question.
Yeah, I have time now, all the time for questions.
Just your minute. During your talking, Julia asked why not make a kind of Bayesian assumption as to what we expect the distribution to look like.
So yeah, one question is, can we make some sort of assumption over how the distribution solution look like? Well, there is no assumption that we know works for all kind of formulas out there. There was a line of work in 2000 that tried to make some assumptions and try to come up with estimates, and that did turn out to be very wrong sometimes. So it is very hard to know how the solutions of formulas are distributed.
Yeah.
But when the problems are coming from particular domain, let's say they are like being encoded of Bayesian network, then of course there is an underlying distribution on which you can make some assumptions. Yeah.
And in the last sentence, it seemed like in the limit you want number of cells to be the same as the number.
I guess I answered that, right?
But then you get the initial problem back. So then why not?
Yeah, no, that's we talked about it. I guess Julia did. I hope once I went to the next slide, everything became clear. Yeah,
So,
this is exactly what I wanted you to wonder about. So yes.
Thank you, Hassan. I was wondering, once we solve the counting instance.
Yeah.
Are there any byproducts that give us more information rather than just the number of solutions? So what I'm looking for is something like max sats, skill sat, might tell us that it's unsatisfiable, but also give us a core that is unsatisfiable. So for counting, you can theoretically imagine something like, okay, you have 100 solutions, but if you didn't have this particular club, you would have 1,000 solutions. And this extra information